Welcome to the lecture on precipitation hardening and martensite strengthening. So, in this lecture, towards discussing the strengthening mechanism of metals, we are going to have the discussion on these two mechanisms, that is precipitation hardening and martensite strengthening. So, coming to the precipitation hardening first. So, what we know that many a times we try to make the ductile matrix or the material having more strength by reinforcing by having the presence of the second phase particles, and it is one of the adopted method. So, that way we do the alloy strengthening. So, one of the method is the dispersion strengthening, in which we normally have two different type of materials. You have one hard particle, and that will be mixed with the matrix powder, and then they are consolidated using the powder metallurgy route. So, that is one of the method that is known as dispersion strengthening. However, many a times we take what we do is that we adopt the method of precipitation hardening. Now, the precipitation hardening means the precipitates are formed because of certain conditions. We have studied about the phase diagrams, and we also know that in many cases when there is solubility limit and when the solubility is low at room temperature. So, in that case you get the supersaturated solution, and then slowly by some mechanism the precipitates are coming up when the material after being quenched will be aged to certain temperature. So, that basically leads to giving the resistance to the motion of dislocation and making the material stronger. So, that is the concept of precipitation hardening. So, many alloy system can be strengthened by precipitation hardening mechanism produced by solution treating and quenching the alloy. So, what we do first is we first solutionize, and then we quench the alloy. So, after quenching, what happens that we are aging at a lower temperature. So, in such alloy systems, the second phase is in solid solution at elevated temperature. So, the this condition comes because the second phase solubility will be higher at higher temperature, but once you go to the lower temperature, its solubility is decreased. Now, when we do the aging further at somewhat lower temperature, then there is precipitation. So, for precipitation hardening, the second phase must be soluble at elevated temperature, but must exhibit decreasing solubility with the decreasing temperature. So, the thing is that in this case that should be the condition. Now, if you so that is why what happens that when you are quenching at a fast rate, or you are making the second phase get trapped into the in the solidified structure, and then further you are when you are aging, in that case the precipitates start coming up. So, basically you have parallelly you have also dispersion strengthened mechanism, dispersion strengthening, where basically this the condition is that even at the elevated temperature they are having very limited solubility. So, but in this case you should have good solubility at elevated temperature, but the solubility is low at the lower temperature. So, that is the difference between these two systems. So, usually there is atomic matching or coherency between lattices of precipitate and matrix. So, that is again there is some difference between the dispersion hardened and the precipitation hardened material. in this case you will have the coherency between the lattices of precipitate and the matrix, and in that case there will not be coherency. And also as we discussed that there will be in dispersion hardness system there will be very low solubility even at higher temperature. So, you are basically having the powders of different materials, and then ultimately you are fusing them together and applying pressure and all that. So, that is what is happening. They are basically they are the distinct phases, and then you are basically getting the required properties by doing the processing. So, what happens, the basic difference between the precipitation hardening system and the dispersion hardening system is that as we have understood that in the case of precipitation hardening system you must have this property that when your temperature is higher, the solute has to be more soluble, and the solubility has to decrease as the temperature comes down, whereas there is no such condition in the case of dispersion hardening. And also we discussed that there is coherency also, coherency has to be there. So, if you talk theoretically, you may have infinite number of dispersion hardening system, because there is no such condition. You can have any material, their powders are to be used and they are to be dispersion hardened. So that matrix is to be made. So, that is dispersion hardened, matrix is dispersion hardened. But in the case of precipitation hardening system, certainly you have some limitation on the number of such systems, because that condition has to be met. So, one of the very example which is live example will be the aluminum copper system. We have studied about the aluminum copper phase diagram also, where we have seen that for a certain copper percentage, and solubility of copper will be up to certain percent, around 5 if you increase the temperature, and if you decrease the temperature, that decreases to a very low value. So, in such cases you have the formation of coherent precipitate in the system, such as so in that case of aluminum copper system. So, what happens that when you quench from the solid solution, the alloy contains regions of solute segregation or clustering. So, basically what happens that when you are quenching the solid solution, and then you will have further aging. So, you will have different stages in which these precipitates are formed, and basically one of the very renowned scientist has worked in this direction, and he has seen the the variation of yield stress with aging time. So, what he saw, so that is Gainer and Preston, that is known as GP. So, that is GP Jones, in fact this has to be Z. So, GP that zone has to be there. So, what you can see that when he did for this aluminum copper system, then what he saw that when this was with aging time and particle size, with aging time and particle size. So, it was seen that how the yield stress is varying, and he found certain curve. So, what he saw that you have he quenched from the solid solution, and it was found that there is a region of solute segregation. So, then what he saw that this clustering, basically initial clustering was seen, and that basically that clustering produces local strain, and in that case, so what he has found the zones, so that is why this is known as GP zones. Now, in that basically he has come to different stages. So, initially he found this theta double prime phase, that is GP1 zone, and then you have the theta prime zone, that is GP2 zone, and then finally he got the equilibrium precipitate. So, towards the end he is getting the equilibrium precipitate. That is theta. So, that is CuAl2. So, this is theta is nothing but CuAl2. Now, what is seen that in this case, so this is your sigma naught, and this way there is the variation of this sigma naught from it goes from sigma naught to theta double prime, and then from there it goes to theta prime, and then further it comes to the the equilibrium phase, that is theta. Now, this coherency which is there. So, after if you age for larger time, then what happens that the particle size goes on increasing, and then after certain stage you have this coherency is basically lost. So, basically that was the observation, and then this is known as the overaged condition. So, in the case of overaged condition, the property basically deteriorates. So, hardness of GP1 will be higher than the solid solution, that is the first zone theta double prime. Now, if you do further aging, then hardness is further increased by ordering of these larger clumps of copper atoms, and this produces increased strain field in the matrix, resulting to increase in hardness. So, you have theta prime stage coming, and then if you do the further aging, then equilibrium phase theta is formed from the transition of theta prime. So, that is what you are getting, the CuAl2 phase, and this is no longer coherent with the matrix, and so there will be a decrease in hardness that is observed. So, if it was if the if you look at the variation in the mechanical properties, then such type of variation was seen. Now, if you draw the stress strain curve for this aluminum copper a single crystal. So, this was the stress strain curve for aluminum copper single crystal. So, that experimental results have indicated that when you have pure aluminum, this goes like so this way it goes. So, this is the so this is your shear stress, and this is shear strain. So, what is seen that so for the pure aluminum, this is the curve, and for the different aging. So, if you go for aging and you have different conditions. So, what is seen is that for the if you go to the peak hardness line goes like this, and for the when the formation of the GP zones, and then in that case it goes like that. And if you are doing the over aging, then it has the curve like this, and in the solid solution you have such is the shear stress strain diagram. So, this is for the aging to peak hardness, and this is for the aging to form GP zones. And this will be for the overaged condition, and this line will be basically once you are coming here, and this is so this is for the solid solution, and this line is for pure aluminum. Now, in these curves basically we are interested basically how this stress strain diagram looks like. Especially this reason, that is this reason when we are just looking at the increase in these stress values, that reason is basically the reason of strain hardening. So, what we see that the strain hardening rate basically, so this is smaller in this case, and it is quite high in the case of overaged solid solution, overaged condition. Now, in the case of solid solution also it is quite flat, and when you are having the aging to form GP zones, certainly we are getting quite high yield stress value. Yielding is occurring at this point, and then you have this is the strain hardening rate. And if you go to peak hardness, in that case what you see that this is the maximum what you see, the strain hardening rate is basically it is continuously increasing. So, basically this is for the shear stress and shear strain curve for the aluminum copper single crystal, and it shows how there is difference in that property once you age, once you are going to age for forming the GP zones or to peak hardness or to overaged conditions. So, precipitate particles in a matrix, that is providing the obstacles to the motion of dislocations. Now, these dislocations moving through the matrix phase either cut through the precipitate particle or bend around and bypass them. Basically, when there is formation of precipitate particles, then either they have to cut them or they have to bend and bypass them. So, cutting through occurs for very small precipitate particles, which can be considered to be groups of segregated solute atoms. So, in those cases it can cut through it, and if there is interface between the precipitate and the matrix, and if the orientation changes abruptly at the interface, in that case the dislocations bend around and bypass the interface particles. So, there are two situations, either they are going to cut through it or they are going to bypass. So, these are the two mechanisms by which the dislocation. So, these dislocation lines when they are moving, they are having the obstruction, and this way once you have the obstruction of the movement to dislocation lines, it means you have basically the strengthening developed. So, that is a mechanism of the development of strength in the case of precipitation hardening system. Now, we are coming to the another kind of strengthening mechanism, that is Martensite strengthening. So, in fact, before that we must have the understanding about this graph, where you have the different type of properties we are looking into. Now, in this case, when the copper is in supersaturated solution, in that case the yield stress is increased significantly as compared to this pure aluminum. So, if you look at this graph, this is pure aluminum curve, and when there is solid solution, then what you see that the yield stress has increased from this value to this value. So, there is a significant increase in the yield stress value, and but rate of strain hardening is basically low. So, that is the characteristic of EG glide or EG slip, and in this case the slip bands are quite wide, broad and widely spaced. Now, if you go to the GP zone formation, one is to form these GP zones. Now, in this case the yield stress, if you look at this is the one where this is the form for the agent to form GP zones. Now, in this case what you see that your yield stress has increased significantly, it has reached to this point, and then there is yield drop is observed. So, from here it is basically there is some drop and then it is coming. So, you find the yield drop, and also what you see that this this strain hardening rate is quite small in this case, it is not very high. So, this suggests that the dislocations cut through these zones. So, we discussed that when the dislocations are cutting through. So, in these cases basically that is likely to happen, and that is why they are cutting the zones. And so, because once the stress reaches high enough value, then they are basically cut. So, that way you have the low strain hardening rate. Now, if you are basically edging to the peak hardness, in this case you are getting the peak hardness. Now, in this case there will be small decrease. So, as compared to this, there will be small decrease in the yield strength, but there is large increase in the rate of strain hardening. So, that is what is seen in this case. And in this case, slip lines were found to be very short and distinct. So that this suggests that dislocations are no longer, now they are cutting through. Okay, and they are basically this is the indicative of the situation where dislocations tend to bypass and have a bend type of movement in such cases. So that is what the situation look like in that case. Now comes the situation where you are doing the further aging, and then you are coming to the overaged condition. Now, in the case of overaged condition, this graph goes like this. So, what you see that again your strain hardening rate is high, but the particles become non-coherent, and the particles become basically rather coarse. So, what you see that the yield strength is low, but strain hardening rate is very high, and in this case the dislocation basically will be accumulate in tangles around the particles in the process of passing between them. So, in that case they promote the slip on secondary slip systems. So, continuously the hardness goes on increasing, and you see a good rate of increasing the rate of strain hardening. So, that is how that tells that how with the different aging time the different type of strengthening can be achieved, and that is what is suggested from this graph. So, next will be so we were discussing about the Martensite strengthening, and we know very much about the term Martensite. Whenever Martensite word comes into, we know that we are talking about a very extremely hard phase. So, it is basically for many systems this Martensite phase, Martensite transformation is dealt with, but mostly it is discussed for alloy based on iron and carbon. So, basically the transformation of austenite to martensite, it is a diffusion less type of transformation process, and in this case the high strength of martensite is basically because of many strong barriers to dislocation motion in this structure. So, what happens that the conventional martensite. So, the thing is that as we know, if you recall the iron carbon diagram. So, in that case you have this structure will be, so you have lower critical temperature. So, as we know that this is 0.8% of carbon is there. So, the thing is that at this point the austenite which is there, this will be converting to ferrite and cementite. Now, the thing is that if you are cooling at a fast rate, then this austenite has the chance to transform to martensite. About that also we have discussed a little bit. Now, we know that this is basically a diffusionless type of transformation there, where shear is occurring, and you are getting so there is large, I mean we have again to talk about how there is interaction and how there is dislocation coming into picture, dislocation lines, and that way the hardness is going to increase. So, this austenite is converted to martensite. So, if you talk about the conventional martensite, so basically you have two types of structures, that is a plate type of structure and block type of structure. So, conventional martensite has a plate structure with a unique habit plane and internal structure of parallel twins. So, you will have the parallel twins which can be seen, and other type of martensite structure is a block martensite, which is containing very high the dislocation density. So, basically what you see is that you have so in this case when you have the twins. So, when you have parallel twins, basically they are about 0.1 micron thick within the plates. So, they are very so that is the dimension of that. And then this block martensite, so they are containing a very high value of dislocation density, maybe of the order of 10 raised to the power 9 to 10 raised to the power 10 per meter square. So, per mm square in fact. So, that is a very high value of dislocation density, and that is corresponding to a very highly deformed material, where the dislocation density basically, because with the change in the dislocation density, the yield stress value will be changing. So, that so that way this basically, so these two, so one is the conventional martensite, and another is because of the so very high dislocation density. So, that is you have the block type of martensite. Now, the part of this high strength martensite arises from effective barriers to slip provided by the fine tuned structures or the high dislocation density. So, as we have seen that either you have the barriers to the slip, that is SLIP in fact. So, this is barrier to that slip which is provided by the fine twin structures or the high dislocation density. So, that way your high strength is coming into. And secondly, the hardness of martensite is also very much sensitive to the carbon content. So, basically what happens that when we do the rapid transformation of austenite to martensite by quenching, then solubility of carbon in iron is greatly reduced. That will produce the strain in ferrite lattice, which is relieved by redistribution of carbon atoms by diffusion at room temperature. So, if you look at the solubility, if you look at the hardness of martensite with respect to carbon, what you see that there is if it is more than 0.4% carbon, then there is a steep increase. Even so, if you the graph suggests. So, if you look at the variation of the graph of hardness versus the carbon percentage. So, this is hardness Vickers, and if this is the percentage carbon, and if you take say 0.2, 0.4, 0.6 and 0.8. So, in that case, if you look at the martensitic structure which is quenched, and if you say this is 100, 200. So, that way if the value is going. So, if your value goes up to say 1100. Now, what is seen that in the case of when there is a change in the carbon content, then the martensitic structure, so that has a hardness increased, and which has 200 Vickers at so say suppose 0% of carbon, and it goes to about the value of 1050 or so at 0.8% of carbon. So, this way it goes like this. So, basically you say so after this what you see that there is an increase. So, with the increase in the carbon content, the hardness is increasing. So, this is basically that hardness or strength which is coming because of the steep increase. So, because you are quenching from austenite and transforming to martensite, which otherwise in normal case there could have been 0.02% carbon, but then you are retaining 0.8% carbon suppose. So, it is about 40 times so about 40 times increase of the carbon concentration is there, and because of that you have increased hardness. And so once you are so as we discussed that when you are doing the rapid transformation of austenite to ferrite, so this carbon solubility will be greatly reduced as the temperature will come down. So, that will produce a strain in the ferrite lattice, and then it will be relieved by the redistribution of carbon atoms by diffusion at the room temperature, and so that there will be a strong binding. So, that binding is set up between the dislocations and the carbon atoms, and that binding, so that will be that will basically restrict the movement of the dislocation, and that way the strengthening is achieved. So, ultimately what we see that because of these interaction, because of the binding, the movement of dislocation is hampered and your strengthening is achieved. So, this is about the Martensite strengthening mechanism. We will talk about the other strengthening mechanism in our coming lectures. Thank you.